Polyprotic acids are weak acids that have 2 or more hydrogen atoms per molecule. For example, H3PO4 is a polyprotic acid. In the first dissociation, Ka1, H3PO4 loses 1 hydrogen to become H2PO4-. H2PO4 can react with water to lose another hydrogen to become HPO4-2-, and then HPO4-2- can react with water to lose another hydrogen to become PO4-3-. And so there are 3 dissociations because there are 3 hydrogen atoms in H3PO4. The dissociation constants decrease with each step, so I get the most ions with the first dissociation, Ka1, and I get the least ions with Ka3. Let's look at an example with a diprotic acid, H2S. So we have H2S reacts with water. In the first dissociation, we're going to lose 1 hydrogen, so you're going to get HS- and H3O+, and this is Ka1. In the second dissociation, HS- reacts with water to give us sulfide and H3O+. So this is Ka2. And we're given the values for Ka1 and Ka2. We want to calculate the concentrations of all species present. So we're going to start with the first dissociation. H2S reacts with water. HS- plus H3O+. The initial concentration is 0.1. Products are 0. We don't know equilibrium, so we're going to use variables. This is the first dissociation, so we're going to use the value for Ka1. Ka1 is 1.1 times 10 to the negative 7th, and that's going to be equal to x times x, and we can use the shortcut divided by 0.1. So x is the concentration of H3O and HS-. And when I solve this Ka1 expression, x comes out to be 1 times 10 to the negative 4th molar. The concentration of H2S is equal to 0.1 minus x. When I take 0.1 minus 1 times 10 to the negative 4th, essentially I get 0.1 molar. It doesn't dissociate very much at all. And then finally, anytime we have H3O, we also have OH. And I would find OH by taking 10 to the negative 14th and dividing by x, 10 to the negative 4th. And so OH comes out to 10 to the negative 10th molar. So there are 4 species that are present in this solution. That's from the first dissociation. There's also a second dissociation. And for the second dissociation, we are starting with HS- reacting with water to produce sulfide and H3O+. Okay, initially, HS-, we just solved for that, 1 times 10 to the negative 4th. Sulfide is 0, but H3O is also 1 times 10 to the negative 4th. We solved for both of these two quantities in the first dissociation, Ka1. We don't know the change, so we'll use a variable. I'll use a y here. So at equilibrium, here are the concentrations of the species that are present. We're going to use Ka2. The value for Ka2 was 1 times 10 to the negative 14th. Sulfide is y. H3O is 1 times 10 to the negative 4th plus y. But we can use the shortcut, so we're going to assume y is negligible. So we're just going to get rid of that. divided by 1 times 10 to the negative fourth minus y, but again, we're going to assume y is negligible, so get rid of that. And you'll notice that 10 to the negative fourths cancel out. Y, which is equal to the concentration of sulfide, is just the value for Ka2, 10 to the negative 14th. So that's how we would solve a diprotic acid. Hydrolysis is the reaction of a substance with water. When a salt dissolves in water, it produces ions, and those ions can react with water. Now, in Bronsted-Lowry terminology, anions of strong acids are weak bases. Anions of weak acids are strong bases. That's an important concept. For example, HNO3 is a strong acid. Its ion is a weak base. Acetic acid is a weak acid, but its ion is a strong base. And that's important when we look at salts. There's 4 types of salts. The first one, salts of strong acids and strong bases. These are going to be neutral when they're dissolved in water because neither the cation nor the anion reacts with water. For example, NaCl. Here's how I break apart salts. When I put NaCl in water, it breaks apart into Na plus and Cl minus. It's aqueous. Na plus comes from the base NaOH. NaOH is a strong base, which means this ion is a weak acid. They're always opposite. Cl minus comes from HCl, which is a strong acid, so it means the ion is a weak base. So if I just have a solution of NaCl, neither one of these ions is strong enough to react with water. So the solution is neutral. Second type of salt, salts of strong bases and weak acids. These are going to produce basic solutions. For example, if I have a solution of sodium acetate, when I put sodium acetate into water, it breaks apart into the ions Na plus and acetate. Na plus comes from the base NaOH. NaOH is a strong base, which means Na plus is a weak acid that will not react with water. Acetate comes from acetic acid, which is a weak acid. It's not one of these 6 strong acids. So that means the ion is a strong base. So this ion will react with water if all I have is a solution of sodium acetate. So the ion reacts with water in this equation down here to produce acetic acid plus hydroxide. So the ion acts as a base. It comes from a weak acid. It acts as a base. The equilibrium constant is called a hydrolysis constant, or Kb for acetate. And the value of the hydrolysis constant can be found by dividing Kw by Ka for acetic acid. Here's the derivation. I'm not really worried about the derivation, so you don't have to worry about this part right here. How do you find Kb if you're given Ka and vice versa? The equations are down here. Kb is equal to Kw divided by Ka. Ka is Kw divided by Kb. So don't worry about the derivation too much. Just know how to get the Ka or Kb value. Let's look at an example. We have a salt of sodium acetate. We want to calculate the hydroxide ion concentration and the pH. Well, as I went through this before, Na plus doesn't react with water because it's a weak ion, but the acetate ion does react with water because it's a strong ion. So my equation is acetate ion reacts with water to produce acetic acid and OH. Initial concentration is 0.1 for the acetate. Now the sodium is still in solution, but it's a weak ion. It does not react with water. Products are 0. We're going to have to use variables here, plus x and minus x. Since acetate acts as a base, I need a Kb value. Well, Kb is Kw divided by Ka. Kw is 10 to the negative 14th. Ka, given in the problem, 1.7, 10 to the negative 5. So Kb comes out to 5.9, 10 to the negative 10th. So now I have Kb, and I can set up a Kb expression to solve for hydroxide. Kb, which is equal to the 5.9, 10 to the negative 10th, is equal to products, x, times x over reactant, which is 0.1 minus x, but I can use the shortcut. So x is the concentration of hydroxide from the equation, and the concentration of hydroxide comes out to be 7.7 times 10 to the negative 6th molar. I also want to find the pH. Well, the pOH would be the negative log of 7.7 times 10 to the negative 6th. So the pOH comes out to be 5.11, and the pH, 14 minus that, 8.89. So this is a basic solution if I dissolve sodium acetate in water.